Hey everyone! In this video, I would like to talk about Rolle's theorem. Rolle's theorem is a theorem that's going to lead us towards a really important theorem in calculus, the mean value theorem. So what I'd like to do in this video is just talk through the theorem, try and make sense of it, show you an example of what it would look like, some examples of what it doesn't look like, and then I want to apply it in a specific example, taking a look at a specific function. So let's just start by reading through Rolle's theorem. It says, let f be a function defined on a closed interval from a to b. If f is continuous on the interval from a to b, if f is differentiable on the open interval from a to b, and if f of a is equal to f of b, then there is at least one number c in the open interval from a to b for which f prime of c is equal to 0. Okay. There's a lot of information in this theorem. Let's just go step by step and make sense of what each part means. So going back to the beginning, we have a function f, and it's defined on a closed interval from a to b. So let's just start in my graph here. Let's pick out a starting point. We'll say that this is a, and then we'll pick out an endpoint. We'll let that be b. So the first part, it says f is continuous on a to b. So that means that there are no breaks in my function. The second part says f is differentiable on the open interval from a to b. The function isn't going to be differentiable at the endpoints, but we want to make sure that everything in between is. So our function is not going to have any sharp corners. It's not going to have any cusps or anything like that. In the last part, f of a is going to equal f of b. This means that the two endpoints have the same y value. So let's go to our graph here. So the last part, f of a is equal to f of b. So that means that my two endpoints have the same y value. So whatever this is here. Now it's going to be continuous and differentiable everywhere in between here. So we're going to have a smooth curve that connects a and b. It can do a bunch of different things in between here. It can go up and down as many times as it would like. I'm just going to do a simple example. We'll go up and we'll go down a little bit. But here is our function, just as an example. So as long as those three criteria are met, then there's at least one number c in this interval for which f prime of c is equal to 0. So what that last statement means is that as long as these three conditions are met, somewhere in between a and b, we can find another number c such that the derivative is going to be equal to 0. That means that the slope of the tangent line is going to be 0, which means that we're going to have a horizontal tangent line at some point in between a and b. And as we can see here, I picked out a c that's going to be at this local maximum right here, where we would have a horizontal tangent line, meaning f prime of c is equal to 0. So that's the gist of Rolle's theorem. We have three conditions that we need to meet. We need our function to be continuous, differentiable, and the two endpoints have to have the same y value. And if that's the case, we know that there's going to be a horizontal tangent line somewhere in between our two endpoints. So now I want to take a look at what Rolle's theorem does not work for. So in each case, I want to show you just when one of our conditions isn't met. So again, let's start off with our two endpoints a and b. So in this first one, let's say our function isn't continuous. Well, a and b still have to have the same y value, but now our function isn't continuous. So for example, maybe we have an open circle here lined up with a, and then our function just goes straight down, kind of curving into b. So our function isn't continuous at one of these endpoints, and because of that, Rolle's theorem doesn't hold. So as we can see just by the way I drew this, we're not going to have any point in between a and b where we're going to have a horizontal tangent line. Now let's say our second condition isn't met. So let's say f is not differentiable on this open interval. So let's start with a and b. Again, our two endpoints have the same y value, but now it's going to be not differentiable somewhere in between A and B. So let's say we just have a sharp corner like this. Okay, so now here at this point, our function is not differentiable, and the derivative at this point doesn't exist. And then as we can see, at the other points, we don't have a horizontal tangent line. And for the last one, let's say that our two endpoints don't have the same y value. So let's put A here, we'll put B up here, and I can just draw a curve that'll go straight up to B, and we can see that we're not going to have a horizontal tangent line. So if one of the three conditions is not met, Rolle's theorem doesn't work, and we can't come to this conclusion. So now that we have an understanding and a visual to go along with what Rolle's theorem is talking about, let's take a look at an example for a specific function. Okay, so my example, I have a function f of x is equal to x to the fourth minus 2x squared plus 1, and we're looking at the interval from -2 to +2. So what I want to do is I want to talk about why Rolle's theorem is going to work, and then I want to find all the numbers in between -2 and 2 that Rolle's theorem is going to guarantee. So the first thing, is this continuous on our interval? Well, my function f is a polynomial, so it's actually continuous everywhere. So it is going to be continuous on this interval. And furthermore, because it is a polynomial, it is actually going to be differentiable everywhere as well. So the first two conditions are met just based on the fact that this is a polynomial. Now for the last condition, we just need to verify that f of -2 and f of 2 are the same. So let's evaluate f of -2, and we'll do the same for f of 2. So if we plug these in, we get -2 to the fourth minus 2 times -2 squared plus 1. So this is going to be positive 16. -2 squared is positive 4. So this will be -2 times 4, so that's -8 plus 1. And we're going to end up with a value of 9. Let's do the same thing for 2, but I can already tell here that we are going to end up with the same value. Because I'm raising this to the fourth power and to the second power, the positive or negative will actually just simplify, and we should end up with the same thing. So 2 to the fourth minus 2 times 2 squared plus 1, and we have the same values here. So 16 minus 8 plus 1, we also get 9. So all three of our conditions for Rolle's theorem do hold. It's continuous, it's differentiable on this interval, and the two endpoints have the same y value. So now let's find each of the values, So now let's find each number in this interval where we're going to have a horizontal tangent line. So to do that, let's take a look at the derivative. So I'm going to start by finding f prime of x, and I can just use the power rule to do this. So the 4 comes down, so 4x cubed, and then if I bring the 2 down, 2 times 2, we get minus 4x to the first, and the derivative of 1 is just 0. So now, where we're going to have a horizontal tangent line is going to be wherever this is equal to 0. So I'm going to take my derivative, I'm going to set this equal to 0, and then let's solve for x. Right away, I see that both terms have a common factor of 4, so we can divide that out. So we get 0 is equal to x cubed minus x. And then I can factor this. So let's factor out an x. And then we have x squared minus 1. And we can keep going. We have the difference of perfect squares. So we can factor that into x plus 1 and x minus 1. So the three numbers, if I set each factor equal to 0, the three numbers where we're going to have a horizontal tangent line are at 0, -1, and +1. And now just double checking those. So we want the interval from -2 to 2. All three of these numbers are within that interval. So that means that these are all the possibilities for the number c, which Rolle's theorem is going to guarantee.